So I promised that last week would be the last class, but I figured it might not hurt just to do a final review session anyway, and so maybe this will actually be the last class. So no office hours tonight, but we will keep the office hours for the rest of the week, Tuesday and Wednesday. Tuesday is going to be at 3 o'clock like normal, and then Wednesday will be the normal time of my office hours, which would be after when class would normally be, so 4 o'clock. And both of those will be led by the TAs. As far as the actual exam, right now on the doodle poll, it is exactly tied between Monday and Tuesday of next week. I'm probably going to flip a coin if some of you guys want to rush in and fill out the doodle poll between now and midnight, let's say. Then I'll announce something later tonight after midnight. Okay. So probably either Monday or Tuesday of next week. Yeah, TAs will be running office hours on Tuesday and Wednesday. Feel free, please do reach out to me if you want anything from me, like if you want to ask me any questions or anything like that. Yeah, any questions right now from any of you? Okay, let me go ahead and start sharing my screen because I just wanted to maybe refresh everyone and shake some dust off after Thanksgiving. No new content here. Like I said, this is just a review session. And no real examples either. It's basically just an overview of what we've been talking about and how it all kind of fits together. Okay, so the basics, let me just start with the basics. If I can get my pen to work. Okay. Basically, the point of the class is teaching you many different ways of calculating flow rates, forces, pressures, and stuff like that. So velocities, right? We're interested in pressures, we're interested in forces, flow rates, etc. And if you think about all the stuff that we've done in this quarter, basically it's all just been trying to further that particular goal. Okay. I'll talk about various ways that we have discovered to find how to find flow profiles, velocity profiles, and everything. But just to remind you, one relation that came up a week ago on Monday's lecture in creeping flow was this, and this is quite important, right? Because once you have the flow rates and everything, then you can use this to calculate stress vectors, and then forces, for instance, you can get by integrating along a surface, right? So you would get something like this, right? In other words, we integrate stresses to find force, okay? Obviously you can also integrate velocities to find flow rates, stuff like that, okay? And so that's basically the point of everything that we're trying to do. To get to velocity profiles and stuff, we had to end up solving Navier-Stokes. And Navier-Stokes depended a lot on, Navier-Stokes is a partial differential equation. And so before the last exam, we talked a little bit about different ways of actually solving partial differential equations. Okay, so for instance, if we were in a domain that was finite, so like this is the classic like flow between two plates or something like that, or on the first exam you had a spin coater where like there's a finite thickness in that in the thickness of that film, right? Like I mentioned, we would typically have a length scale, right? Then you would have a time scale as well. And then the method that we would use is FFT. And you guys have shown that on exam 1, you guys generally know how to use FFT and stuff like that, right? We also encountered scenarios where there was no length or time scale. Scale. Okay. And for that, we would use similarity. This was Stokes' first problem, if you recall. There's also, we also started talking a little bit about similarity solutions when it came to boundary layers, because as you recall, in boundary layers, you're talking also about matching conditions infinitely far away from the boundary layer, right? And so just to remind you, the solution to Stokes' first problem looks something like this, right? We had a Vx, and this was that C thing. Okay. The other example that we did was if you have an oscillating boundary condition, right? If we do that, then commonly we would use a Fourier transform. And that was that table that we introduced, right? And then on one of the homeworks, you actually did this on a mass for a mass flow problem, right? The concentration profile was sinusoidal, and then you had to figure out how it varies with time, right? In fluids, this was called Stokes' second problem. Right? And just to remind you, the solution to that was something like this, right? Okay, so that was all stuff that we theoretically covered before the previous exam. I think we did the Fourier transforms after the first exam, but it's sort of in the same general class of problems. These are called unidirectional flow problems, right? Flow where the PD depends on one dependent variable. In other words, there's only one. The flow is only going in one direction, right? After that, we started to get into something called the lubrication approximation. Okay, that was a another thing that this was called in Dean is called nearly unidirectional flow, right? And the idea there was that we started with, so let's just say a 2D flow, although we can apply this to 3D flows, or the same idea applies to 3D flows if we're trying to eliminate certain things. This would be the Navier-Stokes equation in 2 dimensions. Sorry, that's an X. That, right? And what we showed with the lubrication approximation was that this first viscous term is much, much less than the second viscous term if the length scale in y is much, much less than x, right? And we also showed that the inertial terms were much, much less than the viscous terms if the Reynolds number times the aspect ratio is much, much less than 1. Okay. And so using this logic, we were able to apply this to this this 2D Navier-Stokes equation, and the equations become something like this. Right? This was sort of our first foray into approximation and scaling, right? In trying to show why different some terms are smaller than other terms and stuff like that, and why some terms are important, right? We use this concept, for instance, a lot in the boundary layer case, because in the boundary layer case, again, we saw that the thickness of the boundary layer is much, much smaller than going along the boundary layer, for instance, right? And then, we'll get into that even more when we start talking about perturbation and stuff like that, right? The other aspect of this, which also might seem a little bit more recent than the boundary layer thing, was that the pressure is only a function of x, right? And so the general solution method in lubrication problems looks something like this. One was that we solve for Vx in terms of dp dx. And we can do that fairly easily just by using this equation, right, that we get by applying the lubrication approximation. You just basically integrate this twice, right? But this dp dx is not necessarily constant, and so we don't know a priori what it was, right? And so we had to kind of go in a roundabout way to actually figure out what it is, right? For instance, what we did was we use Vx to find Q, right? Q being like a flow rate, right? And then what we did was we related Q to dp dx. Then we used a macroscopic balance to give dp dx as a function of x. Hopefully this sounds a little familiar to you guys. We did a couple problems like this in class. One where we had a channel that was varying in width as you moved along it, right? And then we said that the Q is going to be constant, obviously, right, along this channel. And so then that allowed us to relate dp dx as a function of x, right? The other example that we did was we had a tube where it was porous, right? And then what we did, the macroscopic balance involved like how much, if you look at a section of this tube, how much of the fluid actually moves out of the walls versus how much actually goes through. And that allowed us to figure out Q as well. Okay. The reason why we would want to relate dp dx as a function of x is because then we can integrate it to find delta p. Obviously, the integral of dp dx in terms of x is going to be delta p, right? And then this then gives us Vx, right? Because from up here, our Vx is in terms of dp dx. And so if we know our delta p, then that gives us what our Vx would be, okay? And then if we cared about the velocity in the other direction, then we can use continuity. Okay. All right. And that was all we really had to say about lubrication. Okay. Any questions at all about that? After we played with the lubrication approximation, then we started to get into perturbation analysis. And the reason we were interested in perturbation analysis is because what we notice is that in a lot of times you can in flow problems when we introduced this, we actually did a bunch of some mass transport problems as well too, right? In a lot of these problems, we can express the equation in terms of a parameter that is either really, really large or really, really small, right? So the example that we did was, like I mentioned, a mass transport problem. Okay, that problem looks something like this. Okay, this is where non-dimensionalization is important, because typically when you non-dimensionalize a problem, then that sort of gives you what that parameter is, right? And then it becomes obvious what that parameter is that's going to be large or small, and also becomes obvious like on a physical setting, like what it means for something to be for this particular parameter to be really large or for this parameter to be really small, right? Now we had two cases of perturbation analysis, right? If our particular parameter here is on the small side, is small, then for instance, in this particular equation, the highest derivative, I cannot spell today using a pen, is preserved, right? In other words, as you can see right here, if this epsilon goes to 0, then you still have a second order differential equation, right? And so then what we have is a regular perturbation. Okay. And the approach in general for this is we basically assume that our solution can be written as a Taylor expansion in terms of this parameter. Okay. And so then we insert this into the equation, and we match powers of epsilon. Okay. A lot of times people forget, and so please do not fall into this trap. You must also do this for the boundary conditions. Okay. And then it's just a matter of solving each equation for each power of epsilon, right? You have an infinite number of equations because you have an infinite number of powers of epsilon, right? But luckily you don't have to solve all of them. You just do as many as you need to get to as good of an approximation as you want. Okay. And so we did this in class with a couple examples. One of the examples was in this particular equation where we actually can solve it. And then, we showed that there's sort of a polynomial to this. I think you also showed in the homework that if you were to actually solve this for real and then do a Taylor expansion, it exactly matches the regular perturbation series, right? And then in class we also did, I think, basically this example, except there was an f² where there actually is no analytical solution. Okay. The other example that we did, that's maybe a little bit more conceptually challenging, is if epsilon is large, then we have to use singular perturbation, right? And that's because we lose the highest derivative, right? That was, for instance, if we look at this, if epsilon becomes really large, then maybe we can divide through by epsilon and then have like a delta here, which is 1 over epsilon. And if delta goes to 0, then we just end up with f equals 0, right? And we no longer have a second order differential equation, right? And so then we have to do singular perturbation. Okay. And this was the scenario where you had to split the problem into an inside and outside domains. I'll say inner and outer domains. Okay. Commonly what we did was, as I mentioned, we can use a delta as being a 1 over epsilon that then goes to 0 for the outer domain, right? If we do let delta, which is 1 over epsilon, go to 0, then in the outer domain, you basically just get the simpler case, right? Where in this case, f would then just be equal to 0, right? The problem with just doing that is that because as we've said multiple times in this class, for every derivative there's a boundary condition. And so if you lose your highest derivative, then you lose some of the boundary conditions and you're not able to satisfy all the boundary conditions. And so this particular solution, f equals 0, is then not able to solve all the boundary conditions close to the surface or something like that, right? And so that's why we had to split up the problem. And so then for the inner problem, what we did is find a new length scale in this particular case. We thought, okay, let's use a y, which is epsilon over some g of delta, right? And we found what our g of delta is to balance the terms in the equation, right? And so we know that in our inner domain, both of these terms have to be important. And so if then we select our function of delta here, in this particular case, it turned out that g was equal to something like the square root of delta, right? Then we showed that both of these terms have to be of similar order, right? So this is another example of where it's important for us to sort of anticipate a priori what terms are going to be important, and then how we non-dimensionalize to preserve those terms in the equation, right? This is sort of, this is kind of related to this in the lubrication approximation. We had a lot of different terms. And what we saw was that, given the scenarios that are given by the problem, like the aspect ratio and the Reynolds number and stuff like that, we're able to show that some of those terms do go away. In this particular case, we know that in the inner domain, these terms have to match one another. And so we actually non-dimensionalize such that that has to be true, right? And then to solve the inner domain problem, what we did is we matched the boundary condition from the inner problem with the outer solution. Okay. And the reason why we talked about perturbation was, well, first of all, it's a useful method. As we know, in most scenarios that you'll deal with, not even in fluids, but just for instance, if you have to solve a differential equation in your research, let's say you have to do a kinetics problem or something like that. If you have to do kinetic modeling for metabolic engineering, I have no idea. Okay. You're not going to be able to solve those problems exactly. And so in many cases, it actually is important to understand perturbation because it can allow you to make some headway in those problems. Okay. We used it in this class because it turns out that the Navier-Stokes equation falls under that purview, right? And so I'll just say this applies to the Navier-Stokes equation, to the Navier-Stokes equations, right? Because one way of writing the Navier-Stokes equations looks like this. And I'll put the little squigglies in here just to emphasize that we have non-dimensionalized this equation already. Right? And once we non-dimensionalize our equation, then there's a clear dimensionless group that pops out. That's called the Reynolds number, right? Which I'm sure you guys are all quite familiar with. Similar to over here, the dimensionless group comes out in front of the lower derivative. Okay. And so then we basically did both regular perturbation and singular perturbation for the Navier-Stokes equations, right? When we did regular perturbation, what you would do is insert a velocity is equal to V0 plus Reynolds number V1 plus Reynolds number squared V2, etc., into this PDE, and then match the powers of Reynolds number. Okay. We didn't actually do this explicitly. What we did was we found that the Reynolds number to the 0 power equation gives creeping flow. Okay. That equation then resulted in something that looks like this. That should be a minus. Okay. And maybe you can see how, like, you know, if I were to insert a velocity expansion into here and I collect the Reynolds number to 0 power terms, then I should get an equation that looks like this, right? And then there are various methods to solve this equation. If it happens to be unidirectional or something, then you can use all the stuff that we talked about up here, right? If not, then you can do the one example that we did on Monday was last Monday was basically flow around a sphere, and then we had to use a stream function. Okay, but generally these are equations that you that you might know how to make some headway into. I will point out, kind of as an aside, I never get to this whenever I teach this class. It actually is interesting when you start to add in the additional terms, right? As I mentioned, you can substitute in a velocity expansion, and then you can try and find the order of Reynolds number to the first power solution. And it's actually quite interesting, and you get some pretty surprising results. But that's just a little bit of a teaser that unfortunately I'm not going to be able to have time to talk about. But if you're interested, come find me. I'd be happy to tell you a little bit more. Okay. The piece that we did a lot of was singular perturbation, right? In singular perturbation, that's what we get when the Reynolds number is large. Part of the reason why we were interested in this is because in macroscopic cases, things that are easier for us to visualize, that's when the Reynolds number is actually large, right? And we spent several weeks talking about inviscid flow. We even introduced that in the context of vorticity and irrotational flow, if you recall, right? And then, of course, boundary layer theory, right? The inviscid flow scenario, for instance, we had to solve an equation that looked like this. Although it turned out that we didn't really solve that equation that much, because we started talking about irrotational flow, and it turned out irrotational flow was much easier to conceptualize than this particular equation. Okay, and so that actually brings me to my next topic. And that was this idea that because inviscid flows are irrotational, might want to review and figure out why, or just remind yourself why inviscid flows are rotational. It has to do with a vorticity transport equation, for instance, right? Then we came up with several different methods for actually figuring out how to solve irrotational flows, right? One of those was using a potential function. Okay, so I'm going to copy basically a chart that or a summary chart that I came up with for remembering potential functions and stream functions, which is the next entry in this chart, because it's quite important and sort of helps you conceptualize like how the different solution methods all work with one another, right? The definition of the potential function was that the potential function is just given by the gradient, or sorry, the velocity is defined as the gradient of the potential function. So the potential function is just a scalar field, right? And the reason we do this is because this definition automatically satisfies the fact that the velocity is going to be irrotational, right? This is the irrotational condition. Okay, and this is just mathematical, because if a velocity field is the gradient of a scalar field, then the curl of that velocity field is just going to be 0. And so therefore, in this case, it's going to be irrotational, right? But then in order to actually figure out valid potential functions, then we had to satisfy an additional requirement. And that additional requirement was that we had to satisfy the continuity equation. Continuity equation says that the divergence of the velocity has to be equal to 0. And so therefore, the divergence of a gradient has to equal 0. And so then the Laplacian has to equal 0. And so then it just became a matter of solving this particular equation applied to, for instance, our particular boundary conditions that you care about in whatever problem you're trying to solve, right? The other case that we talked about was the stream function. That we called psi. It's not really another case, it's just another equally valid approach, right? And that also had basically similar ideas here, right? The stream function also was defined in such a way like this. And the reason it was defined that way is because this definition automatically satisfies the continuity equation, right? But then remember, we're talking about irrotational inviscid flows. And so in order for a velocity profile defined by the stream function to be irrotational, then that meant that the stream function also has to satisfy that the Laplacian is equal to 0. And so then again, this gave us another equation for figuring out what the stream function would be that you could then take derivatives of to figure out what the velocity was. Okay. Both methods are perfectly fine to use. Okay. There are benefits and drawbacks to both methods. For instance, the potential function works in 3D. Right? Because in 3 dimensions, you can take the gradient of a scalar function. Right? You can take it in as many dimensions as you want, in fact. Right? But of course, this is only useful for irrotational flows. Right? And that's just because the definition of the potential function says that you are in an irrotational flow scenario. Okay? Stream functions only work in 2D because the definition only has 2 dimensions, right? But because it applies to the continuity equation, or because the definition automatically satisfies the continuity equation, not irrotational, it means you don't have to only apply this irrotational stuff too, right? So we can use this non-irrotational situations. Okay. And I'll just remind you that the definition changes in other coordinates. Okay. And so as an example, we talked about creeping flow on Monday. And in creeping flow, we actually did use the stream function. Clearly, we're not talking about irrotational flow and inviscid flow when we're talking about creeping flow, but we were still able to use the stream function because the definition of the stream function satisfies continuity. And this additional requirement is what gives us this particular equation for irrotational flow, but we can solve a potentially different equation if we're interested in a non-irrotational scenario. Okay. Given these definitions, we did several scenarios of flow past an object. Right, I think in class we did a cylinder for potential flow. I think on the homework you guys did for a sphere, right? And there, the solution methods were, we first determined what the boundary conditions were. But we determined those boundary conditions, or we translated those boundary conditions for phi or psi, for the stream function or the potential function, whichever one you happen to be using, right? Using the definition. Okay. So in other words, you guys already know how to like apply the no slip boundary condition or a no stress boundary condition or something like that, right? But then you have to use the definitions up here to then figure out how that then translates into psi or phi, right? In many cases, it was convenient to convert, let's say, some of the unit vectors. In many cases, our flow was in the z direction, right? To other coordinates, right? To cylindrical or spherical coordinates. Okay. These are one equation, one partial differential equation that you have to solve for either psi or phi, right? And so we can solve those. You guys know how to solve partial differential equations. That's what all this stuff was, right? But when we actually were doing this, we didn't actually use any of those scenarios, or we didn't actually use any of those methods because we kind of took shortcuts, okay? So I'll remind you that you can use those methods if you need, right? But the shortcuts that we were able to take in many cases was that we inferred a form of phi or psi from the R goes to infinity boundary condition. Right. This was where we said like, oh, okay, maybe phi is equal to some function of R times sine theta or something like that, right? Remember, partial differential equations are not easy to solve. You guys know that FFT is laborious, right? And so we're basically trying to figure out ways to translate those into ODEs. And so if you insert like f of that phi is going to be equal to some f of R times sine of theta, then you get an ODE for f, right? And then those were the ones that we were able to solve, right? So in other words, the other thing was that we had to then solve for the radial component, the f part. Okay. And then the other piece was if we were interested in, for instance, how much force does the flow exert on the object or something like that, then we care about, in the creeping flow case, for instance, we cared about the velocity because then you could use Newton's law of viscosity to calculate the shear stresses, right? Here we're talking about inviscid flow, but same thing applies. You also need the pressure, right? So I'll just say use Bernoulli's equation, which is this. Use that to find the pressure. Okay. Some sort of general things that we talked about in inviscid flow was that there's no drag force in inviscid flow, right? This had a name, or this phenomenon had a name. It was called D'Alembert's paradox. Right? And then, of course, we also had other methods of doing inviscid irrotational flow, right? We talked a little bit about complex analysis. That was like maybe one lecture, 1.5 lectures. Okay. And the main takeaway from that one lecture was just that all analytic functions describe some inviscid irrotational flow. And the reason is because if you just write down some analytic function, remember analytic just means differentiable, which for our intents and purposes is just basically any common function that you might find, right? That can be written such that the real part is the potential function of some flow. And the imaginary part is just the stream function. Okay. And so we did like a scatter shot of examples. Just showed you several examples, like for instance, if f of z equals z, then you just got uniform flow in one direction. If you got like f of z equals z squared, then you had some sort of stagnation point flow or something like that, right? Hopefully it sounds familiar to you guys, right? The other thing was that you can replace with walls, streamlines with walls, right? And that's just because the specific case of inviscid flow, right? There's no shear near a surface. And so, if fluid is moving parallel to something, then you can just say that it's it doesn't really matter. Like one piece of fluid along one side of the wall isn't even going to know what happens to the fluid on the other side of the wall, right? Okay. And then the last bit of stuff that we did in the inviscid flow scenario, in the inviscid flow case, was then boundary layers. And so there's not much to say for me here about boundary layers, besides just, some conceptual ideas. The math was laborious, if you recall, right? But it wasn't stuff that you guys hadn't seen before, right? What we saw was that it looked a little bit like the lubrication approximation. Okay. I'll say looks a little like lubrication, where we were able to eliminate where we show that the boundary layer is much, much less in length than the length of the object, then implied some boundary layer equations that then showed that the velocity in the y direction is much, much less than in the x direction. So the velocity perpendicular to the boundary layer is much, much less than along the boundary layer, right? And we also showed that the pressure is only a function of x, right? Those boundary layer equations then, we were then able to solve using similarity solutions, right? But if you recall, the math got pretty laborious pretty quickly. We also had to use a stream function scenario to solve some of those as well, right? We ended up with like third order differential equations and stuff that we actually couldn't even solve analytically. Okay, but we talked about two specific examples, and I can talk to you a little bit about the qualitative behavior of those. So we did talk about flow past a plate. Okay, in that particular case, the boundary layer increased in thickness as you went along the plate, as in at the front of the plate, the velocity goes from u out far away to 0 over a very short distance. But as you move along a plate, the velocity becomes a lot more gradual. Okay, and I hope you guys did get a chance to watch that video that I sent out that really illustrates how this stuff works. Okay. One of the things that matters a lot in boundary layer theory is the thickness of the boundary layer, right? So in flow past a plate, the thickness is some delta scales as nu x over u, right? And this nu x over u basically says what? The thickness actually increases with the square root of x, and it decreases with the square root of u. Okay. Just to remind you, we figured this out. We figured out this using a similarity solution and also a singular perturbation case, right? Boundary layer is basically just a single perturbation case. We basically did this, right? In the inner domain, we redefined a new length scale that's going to be some, length scale over g of delta, and our g of delta showed us that it's going to look that the thickness looks something like this. Okay. We also did a stagnation point flow. In that particular case, we have a plate that looks like this, and the streamlines come in like this, or the flow comes in like this, right? And in that particular case, we also looked at a boundary layer. But it turned out that the boundary layer had a constant thickness. Okay? All that was different is that, for instance, at some point over here, we have a boundary layer, and then some point a little bit farther away, we have a thicker boundary layer, or sorry, not a thicker boundary layer, a higher flow outside the boundary layer. And that's just because, well, like I mentioned, outside the boundary layer over here in the stagnation point solution, the flow here is higher. is stronger. Okay. And one of the lessons that we saw from this particular example was that the thickness here is constant. That constant happened to be something like nu over alpha, where alpha was like the intensity of, or the strength of the stagnation point flow. Remember, Vx is equal to alpha x, Vy is equal to negative alpha y, right? That basically defined the overall speed of the flow. And this is because of what we called a favorable pressure gradient. Okay. And then we talked a little bit later on about the different scenarios of favorable versus adverse pressure gradients. In this particular case, we have a favorable pressure gradient because we have a high pressure here where there's a stagnation point, right? Bernoulli's equation says that the pressure is a little bit higher where the velocity is lower, right? And then lower over here. And so when the flow is going from an area of high to low pressure, then the thickness decreases more, then the thickness increases more slowly than in the flow past to plate scenario. And in this particular case, it's actually exactly balancing such that the thickness is constant. In the case of an adverse gradient, which we didn't actually talk about mathematically, an adverse pressure gradient causes the thickness to increase and then eventually separate. Okay. All right. And that was ChE421. Okay. That was all I really wanted to cover with the review session. Were there any other questions?
I just want to clarify that for the boundary layer, in the two situations, there's still Vy, right?
Say that again. There's still what?
On,
There's still y?
On like the velocity in the y direction.
Yes. And we spent a little bit of time on this, but not very much. You can like, in general with these 2D flow scenarios, we end up using the stream function, right? And so once we have the stream function, then you can either take the derivative in the y direction in order to get Vx, or you can take the other derivative. The other thing is once you have Vx, you can also just calculate Vy using continuity, right? In the boundary layer case, because Vy is much less than Vx, then it doesn't really matter quite so much, right? You might remember a diagram that I drew at some point in the flow past to plate scenario where I had a few up and down arrows over here, and we showed that the velocity is a little bit higher in the front, in the y direction, than it is in the back. Those were less, like the velocity in the y direction is much less important, both because it's smaller and also because, for instance, we care about like shear forces on the plate, right? And those shear forces come about because from Newton's law of viscosity is dVx dy, right? Most of those shear forces come about from the variation in the x direction, not in the y direction.
Okay, thank you.
Yep. Any other questions?
We also covered creeping flow at the end of the class.
We did. Yeah, I'm not talking too much more beyond that. First of all, just because it's kind of fresh in your memory. And so I didn't really need to spend, hopefully didn't need to spend all that much time basically reviewing what we talked about in just one lecture prior. The other thing is that the solution methods look very similar to all the other things, right? If you might recall, creeping flow past a sphere, the solution methods looked very similar to potential flow past a cylinder or something like that. It looked like basically, determine the boundary conditions, infer a form, and then plug it in basically. Obviously, you can't do this in creeping flow, right? Creeping flow also is, if it happens to be unidirectional, then you can use all of the stuff that we did up here to do that as well. Okay. And then, of course, conceptually, creeping flow looks a little bit different as well. Go back and review that lecture. Basically, this was that sort of weirdness with the curved balls and then the objects in different, like if you oriented in different ways, then it doesn't seem to matter, stuff like that. Okay, any other questions? All right. You have 8 hours to respond to the doodle poll if you haven't already. As I mentioned, it's probably going to be either on Monday or Tuesday if you have a strong preference one way or another. If it turns out that you're going to be like traveling or incapacitated during Monday or Tuesday, please let me know and I'll try and figure out something. But I think hopefully you guys should, even if it wasn't your preferred option, you should still be able to take the final. Okay. All right. Thank you guys. I'll see you guys on the final then. Take care.
Thank you. Have a nice day.
You too. See ya.